This screencast will show you how to start a convection problem in heat transfer. And convection is the energy transfer between a surface that's usually a solid and a moving fluid. And generally, the governing equation is Newton's law of cooling, where the heat transfer Q, convective, equals h bar, which is the heat transfer convective coefficient, times the area times the difference in temperature between the surface and the moving fluid. So the equation by itself seems innocuous enough. However, this difficult part is finding this H, or this convective heat transfer coefficient. In order to find H, we use a correlation that is determined empirically or analytically. The secret is to find the correct correlation. And by the way, sometimes it's a matter of the best correlation for a particular situation, as there may be more than one possible correlation. Let me show you the best approach for finding the right correlation. So the first part is, what is the geometry? There are different correlations for different geometries, and what we'll usually be looking at is something like a flat plate or a cylinder or a sphere. So the first thing you determine is, which of these is it? Secondly, fluid properties change sometimes dramatically with temperature, so it's important to pick the correct reference temperature to look the properties of the fluid up. Usually, we look at what's known as the film temperature, which is the temperature of the surface plus the temperature of the fluid divided by 2. However, some correlations have their own reference temperatures, so you need to know what they are and use them accordingly. In fact, in some of them, they even use the free stream temperature or the temperature of the fluid as the reference temperature. The third thing is to calculate the Reynolds number. The Reynolds number is essential to not only determine the flow regime, you also need it to figure out the proper correlation for your situation. Even before you start looking for a correlation, you need to calculate this Reynolds number. The next question to ask yourself is, do we need a local or do we need an average heat transfer coefficient? And if you look at how they're actually written out, the local heat transfer coefficient is just H or H sub x, so it's appropriate for any x. The average coefficient has a bar over it. The correlations are different depending on which one we need. So the local one right here looks at a particular point, usually on a flat plate, and calculates what the heat transfer is there. The average heat transfer coefficient is used to measure the heat transfer along the entire plate. Finally, after all that, we pick the appropriate or the correct correlation based on everything I've talked about above. Notice that these correlations are usually not for H. They are usually for what's known as the Nusselt number. And this is the ratio of the convective heat transfer to the conductive heat transfer. And this equals H, which is that convective heat transfer coefficient, times L, which is the characteristic length, generally the length of the plate, divided by the thermal conductivity of the fluid, not of the surface. This is the thermal conductivity of the fluid. Therefore, if we're trying to find H, it actually equals the Nusselt number times this K sub F divided by this characteristic length. You go through all the steps that I've shown you above, and from that you'll get a Nusselt number, because that's what the correlations are for. Once you get the Nusselt number, you can put that into this equation, find our average heat transfer coefficient, and then find our heat transfer. So the simplest example that you might find for a Nusselt number correlation is some constant, Reynolds to the M Prandtl number, property of a fluid, raised to the N. And these C, M, and N, they vary with geometry as well as the type of flow. And these constants are determined experimentally.